Okay. So I moved the test to Wednesday. We will go over the last couple sections of this chapter, reaction mechanisms and analysis. We'll leave some of the more sticky stuff out, and maybe we'll come back to it. And then I'm going to kind of start chapter 13, which it's on equilibrium, chapter 13, but I promise it's not as sticky as kinetics. So what would I say here? To start with, I wonder if y'all have seen this before. If I said, so this reaction, 2O3 becomes 3O2. All right, and it implies that you have these two things just sort of spontaneously become these three things. So this is like an overall reaction. The idea of a reaction mechanism is you break it down into steps that actually do occur. So this is just very general statement. You can break that down into these two steps. O3 splits out into O2 plus oxygen, and those two steps. So one of the O3s breaks into an O2 and an O, and then another O3 bumps into that O and forms two O2 atoms. You see that? See what I'm saying? Those are two explicit steps that could occur that would cause the reaction to go and actually create three of these. One of the things about this when you do it in steps, you can kind of add it the way you would in do arithmetic in grade school. You cancel out, if there's something that shows up on both sides, this, you cancel them out and you bring everything else down. Notice there's no O2 over here and there's no O3 over here, so I'm not canceling any of those. But this, it shows up, I'm canceling that out and I'm just bringing down what's left. I have two O3s and 1, 2, 3 O2s, and that's kind of a double check just to prove that it does come back to this equation. So if you can take this reaction and split it into what we call elementary steps, it should still add up to the main reaction. And once you have the elementary steps, that's the reaction mechanism. It's the specific mechanical way that the O3s go about becoming O2s. All right. This is called an intermediate, intermediate, I guess. And these are called the elementary equations. And this is called the overall equation. Really kind of where this goes is, well, let me do a couple more examples of these. Here's an elementary step, elementary equation. Here's another one. So this is NOCl2, this is NOCl. So notice the difference there. So what this is saying is, similar to over there, the first reaction occurs and creates this with the Cl2 on it, and then that Cl2 now exists, the NOCl2 now exists, so now that can undergo another reaction with another N to do this. So there's two steps, and if you add them up, so NOCl2 NoCl2, and that's it. There's no Cl over there, there's no NO over there, and there's no NoCl over here, so I can just bring down what I have. I have two NOs, a Cl, two. What am I missing? It's not balanced. Oh, there's supposed to be a 2 there. And here's another example. An NO2 and another NO2, those can become and you can have NO3 react with a CO, give, if you want to know the overall reaction, NO3 is an intermediate. It's created here, then it's used up again over here, down here. NO, NO2. So now this reaction is and again, this reaction down here, this one down here, this one down here, is the way you're used to seeing reactions all the way through last semester and this semester. This chapter is about breaking it down into the mechanism that actually makes it happen. I'm going to keep it kind of that general. So relating this back to rates, when you had a reaction like this, and we did all the stuff about rates and integrated rate equations and stuff, that actual rate, whatever, and what the N and N was, that has to be experimentally determined. Like we were looking at data, and I would say, here's data from an experiment. You would have to get all into it to figure out the actual rate and what it's based on. That's these, but the elementary equations, you can get those just by looking at them. I'll write these here. This is really pretty simple. We're not going to get too deep into this. It's called the molecularity. For instance, a unimolecular would be A becomes some products. And it's basically, that's probably going to be decomposition. Whatever A is, it splits into some pieces over here. There's other things that can happen, like the molecule can rearrange, so the way everything's connected up, it can sort of spontaneously swap some things around and rebond it is different. But just think of this as decomposition. I might have written it as, and then whatever this is decomposing. And you can look here and go, okay, the rate is K, first order in A. You can tell that just by looking at it, first order in A. There's bimolecular, and that would be something like 2A becomes some product, or A plus B becomes some products. And you don't have to do experiments. This one's rate would be rate equals K, A. There's 2 here to make it second order is literally because there's 2 of these that have to bang into each other to make the reaction. In some sense, this is probably the opposite of this. These 2 things, well, if they were the same thing, Or if it's two different things that make product, then the rate would be K, A, first order, and A and B. So that would be bimolecular. They do also one called termolecular. You might guess that's three things. So the molecularity here is 1, molecularity here is 2. There is such thing as termolecular. So an example is, there's not many of these. This one is K. Here's another one. So those examples, and I think that's straightforward and obvious. Realize if you're being asked a question about something like this, like what is the molecularity of this reaction? You would have to be told that it's an elementary reaction to tell you that this shows clearly exactly what happens. It's not some general thing with other steps in between. So you don't have to decide yourself whether it's elementary. Or if you see it stacked like this, these are elementary equations. So we could look here and go, the rate for this first part is bimolecular, and this rate equals K, and then 2, because there's 2 of them. And this one's bimolecular, it would be rate equals K, concentration NO3, concentration CO. So you can't directly see the rate. If you know the mechanism, you can split it out like that. You know the rate here, you know the rate here. And you can use these to build a rate down here. I'll only do one example of that. More examples of that is what I want to say till later. This book really doesn't go into it very well. But I got, in my PowerPoint, the next page I have, and these are really simple. If you saw Cl2 plus CO, Cl2, CO, and then I said this is an elementary equation. Give the following reactions. Oh, okay. Let me do these first. Let me not do those yet. I'll do this one. Number 72. Write the rate law for these. And it's really as easy as this. You had this O3, O2 plus O, and I said that's an elementary reaction. What's the rate for this one? Is it unimolecular, bimolecular, termolecular? This one is like this. It's only got this one reactant. So this one's rate. That's the rate for this. It really is that simple. You guys catch on to this? It is that simple. Pick another one. Cl plus O2. So unimolecular, bimolecular, termolecular. Huh? 2, bimolecular, because of those two. And the rate is just first order in both of those. That's the rate. See what I'm doing?
How do you know it's just bimolecular also first order?
Well, it's first order in ClO2 and it's first order in O, because these are essentially ones. It is overall second order.
How do you know that it's like you don't put the numbers after like the CL?
This is just how elementary equations are. These are second order. You got a 1 there, a 1 there, you add them up, you got 2. This is second order for a bimolecular. It's always going to be first order for these. These, they don't have to bang into anything. It's just the rate depends on how long it takes one to just come apart. You getting this? And then term molecular, there would be 3 things. I erased the term molecular one. About. They didn't put an example here. Can you think of why the 3 molecularity 3 one is really rare? Having 2 things bumping each other is just 2 things bumping into each other. But 3 things, you have to simultaneously get 3 things in the same space bumping into each other. And that's why they're kind of rare. Reactions that go like that are kind of rare. That's really not all. Let me give you one application for this idea. And then I'll talk about catalysis. So let's say we have did I not put it in here? You know what? Yeah, I did. All right, if this overall reaction, and if I ask you a question about this, you don't have to come up with mechanisms. I'll tell you that. Let's say you have this. In this, that you were told that experimentally the rate this is just in the wording. If you knew this, that's the rate experimentally. Right. And then you're asked to, this is just in the wording, but you're asked to find out if it's consistent. So somebody proposes a mechanism. It goes this. You get NO3, NO, then you get NO3 continues to react with some CO. Okay, and here's the only thing I'm really adding here. We've also said that this is, that part of the mechanism takes a long time to happen. And this is really fast. When that's true, the overall rate is going to be based on this one step. So you got this step and this step. This one goes really slow. This one goes way fast. So the rate is going to be based on this, only this step. And if I said, what is the rate law here, you would go, it's bimolecular. They happen to be the same thing. It's rate equals K times NO, 2, NO2. But really, because those are the same thing, what we would really write is rate equals K, NO2, 2. That's the rate for that. And that's going to turn out to be the overall rate for this. And then you would go, yes, if that's the slow step and that's the fast step, then this rate is consistent with the measured rate of this reaction. Don't overthink that. That's really all there is to that. There's variations where there's a fast first step and a slow second step, and there's variations where we have equilibrium. But I'm going to save that until we do the equilibrium chapter, until we're complete. So continuing with any other variation of this will be on test 2. And that stuff about being consistent with the measured rate of reaction is just all in the phrasing. Because you can't just propose a mechanism and then say, okay, I'm going to say that's elementary, and then I'm going to put that rate on it, and that's necessarily true about this. This all has to be done by experiment. And let me do this one more time. These two steps represent this equation. NO2, NO2. I have another NO2 here, but nothing else to cancel it, so I have to leave that one. There's no CO over there. There is an NO3. There, so we bring everything down. We've got an NO2, got a CO. Here I've got CO2, NO, and yeah. These two steps do add up to be this overall equation. That's all we'll do with this mechanism stuff. So now I guess I can do 71. 71 doesn't give you all the answers, but this stuff isn't hard. I have one of the steps for a reaction. And then it says, this is one of the steps, one of the elementary equations. And this is the overall measured rate CO2. I did mention the other day that you can have fractional things like this, but we're not going to deal with those the way we were the other things. And the question is, if this is one of the elementary steps, and this is the overall rate for the equation, if this is the slow step, slow is it's called the rate limiting step. Rate limiting step, rate something step. But the rate limiting step, if we try to say this is the rate limiting step, that means the overall rate has to be consistent with it. So that's the question, yes or no, is this consistent with this? Well, this is just, this equation is just, it's bimolecular. So it's not, we technically have ones here, so that is not consistent. The next question says, how about this one? PCl3 plus Cl2.
Wait, so is the rate equal to CL2, CL, is that just like the second step?
Yeah, well, it's being considered, this is the slow step. If we've come up with a mechanism and we said, I think this is the slow step, and then somebody says, well, I've done this overall reaction, whatever it is, and this was the rate I came up with. And the question is that consistent with this being the overall rate? And that would, if it is, then this has to be exactly the same as this. These two have to be exactly the same for it to be consistent with the overall reaction. The question says, given the following reactions and the corresponding rate laws, and which reactions might the elementary reaction and the overall reaction be the same? And they're just giving the elementary reaction. The next one says this, and it says the rate for this reaction well, the rate for this reaction would be this. It's so long. This is PCl5. So is this consistent with this? And basically, you're just looking for the bimolecular So, and it is, because you've got this here with a 1, you've got this here with a 1, yeah, that's consistent with that being the overall rate. So you're just seeing if, you basically take this, you write the molecularity rate equation. And if it matches this, then it's yes, it's consistent. Alright, that's enough of these. I might not even put that on the test. It fits in a larger discussion. Let me go on to catalysis. Catalysis. You know what catalysis means? You know what a catalyst is? So you have a reaction, it goes a certain speed. If you have that same reaction and you put this other stuff in there, it goes faster. Catalyst just makes it go faster. But there are some other conditions, like it can't get used up in the reaction. But let me say this first. You remember these diagrams? We call it extent of reaction, but this is the reaction going. It's like right here are the reactants, and then it goes for a while, and then you get some products. And we usually do the energy like this. This is the energy. And the key here is, so you have reactants, you have products. Maybe you remember that the difference between where this is on the energy and where this is on the energy is delta H. That's not the discussion we're going to have here. That's just a reminder. And if it does this, since there's more energy in there than the start, this would be endothermic. I could make this come down here and go below here, then it would be exothermic. But the key here is level with this point, the reactants. The distance to this peak, do you remember what I called that the other day? We go EA, that's the activation energy. That's how much energy has to go into this to make it occur. Remember that? All right. If we did the same reaction again, we need to start here and end here on products. So this point and this point is the same, and there's still going to be a hump. But if I did this instead, I did it again, I put something in there to make it go faster. These peaks don't even have to line up with time. The fact that that is lower in energy activation than that tells you that's a catalyst. Same exact reaction, but now the energy profile looks like this. That tells you that this is the reaction that had a catalyst. It's probably worth mentioning. Sometimes catalysts make more than one step. And I'll make this endothermic again. There's that, and then they show the catalyst like this. And all that's saying, these are different steps. Like the steps I was showing before, the catalyst introduces a couple of steps instead of just going in one step. So you still have a catalyst here, and it's still decreasing energy here. Probably a little better. Do that. So you see two steps here, but still the rate limiting step is this. So that's the key. The higher step is the rate limiting step. That's the one that takes longer. The higher peak is the rate limiting step. And it's reduced that rate, the energy of the overall reaction. That's kind of all I want to say on this. One other point to make about this. Do look at exercise 12.16, 12.15. So they're showing, this is easy. They're showing, here's a reaction, and they've got this ruled off nice and neat. And they're calling it kilojoules of energy, but they show 0, 5, 10, 15, 20. And then they've got another graph. It's got the same, if I just went straight across, that's 5, that's 0. 10 is about here. So they have the rule, the tick marks all the way up. And this one does something like, and this one does, and clearly this is the catalyzed reaction. This is the reaction without the catalyst. And they ask you to estimate the activation energy. To do that, all you need to know is, here's where your start line is, your end is here, and then you're going, okay, this is about 6, and this is about whatever it is on here. Let's say about 33. So 6 to 33, or that is 33 minus 6. That gap right there, minus 6 is, what is that, 27? And then you can do it again over here. The key is knowing that you're measuring from here up to wherever this is. And then you'll get a smaller gap, and you'll say this activation energy is this bigger number, and this one is smaller. But look at those rulers and see if you can estimate that. I guess that's good. The Check Your Learning one just has 2 humps for it. The Check Your Learning one, do look at it. I'll put one like this on D2L. It shows, this one actually goes exothermic. And then they show the catalyzed one. And basically, this hump looks the same as this hump. But this hump has been dropped here. And that tells you the first step is the rate limiting step. And that it's that step that's being catalyzed in the reaction. You see that? That's not part of the rate. It's all just conceptual. You guys okay with that?
Would you be able to repeat that?
Huh?
Would you be able to repeat that?
The Check Your Learning one for 1215 has the same energy diagram set up. It shows you this for the uncatalyzed reaction, and this for the catalyzed reaction, and the only difference is the height of this first hump. So it tells you that the first step is the rate limiting step, and it's that step that's being catalyzed that is dropped in energy to this. So this is catalyzed, this is uncatalyzed.
Oh, okay, thank you.
I did put, I don't know how to ask a question like this. Because they don't phrase this very well in the end of chapter. End of chapter 78. But let me write this down. So there's one step for the reaction, another step. Two. ClO plus O. All right, if I took this and I said, you know what, I want to know what this overall reaction is. ClO, ClO, O, O. There's a Cl I can cut out. And look what I've got. 2O3 becomes 3O2. That was the first example I wrote up here. So what you can tell by this, if you're given all these steps, is A, you can see that this is the overall reaction. And if you're told the reaction went faster when some Cl was put in there, then you can go, okay, Cl is a catalyst, but there's a key here. Cl is used here, it becomes ClO. And then when you get down here, the ClO reacts and you get the Cl back. So this is the key. A, you're told it goes faster when you put some Cl in there. And there's stuff you could put in to make it slower. So it isn't necessarily true that this is faster. You would have to be told that. So the reaction goes faster when you put some Cl in there. But the key here is the ClO shows up as an intermediate, and the Cl gets used up. And if you look at this, you go, this happens, and then another O3 reacts with Cl, and this happens, and this goes on to react with some O. This happens. The O is produced up here, the ClO is produced here, and then they react, and you go, where's the Cl? When it comes to a catalyst, we do this. I'll say Cl atoms. You write the catalyst up there. So in case you're looking up here and go, where's the Cl down here? It didn't show up. Well, if it's the catalyst, you write it up here like that. And the ClO is just an intermediate. So this question says, explain why chlorine atoms are catalysts in this gas phase transformation. And if you look at the answer key, it says, because Cl is brought back to its original form here. So you could add Cl here, but by the time you get all your O2 reacted, there'll still be some Cl there, and it'll be exactly the same state it was in when you first put it in. If Cl got transformed somehow, it's no longer a catalyst, it's part of the reaction. I don't know how to ask that, but I think they phrased that too weird. But you would have to be told, you're told that it is a catalyst, and then you explain why is it a catalyst. Well, it's a catalyst because it makes it go faster. But one condition that catalysts have to have is the condition they went into the reaction in, they have to come out of the reaction just like that. They can't be used up or consumed or changed or whatever. And there's another example there in 78. O3, it's another catalyst for this reaction. How would I phrase this question? One thing I could say is, what's the overall reaction if those are the steps? And you would have to go through, there's NO2, there's NO2, there's NO, there's NO, there's O, there's O, nothing else cancels, and I have 2, O3, to 3, O2. And if I tell you that this reaction went faster with these as its mechanism, you could say, okay, NO is the catalyst. NO2 is an intermediate, because O3, O2 to O, there's no NO here, or NO2. It's here that first that the catalyst gets involved. So you get this as an intermediate. Intermediate. And this was the catalyst. It showed up here as NO, and that nitrogen and oxygen showed up here again as NO. So NO is the catalyst, NO2 is the intermediate. And this is the overall reaction. So that's the way I might ask this. I'll give you some steps and say, A, what's the overall reaction? B, where's the intermediate? And C, what's the catalyst? You see the logic there? The catalyst first reacts here. NO2 shows up here, gets used up here. So that's an intermediate. And the NO is the catalyst. Adding the NO is the catalyst. All right. We'll probably go pretty short today. I really just want to explain the concept of equilibrium. So this starts chapter 13. school or wherever you took this, equilibrium? Just the word and it came up in class. Did you hate it? No? Tell the truth, did you hate it? I hated it the first time I saw it. And this is why I understood that becomes, I'd gotten to this point in chemistry where I was like, that makes perfect sense to me, and then I start going, oh, but this, and with a double arrow. So a quick explanation of what equilibrium is. So there are a lot of reactions that do that. You put in some reactants, they react. After a little while, you have products, and all of the reactant is gone, you have all products, and that's all we've talked about so far. But it turns out many reactions, important reactions, a lot in biology of this. If I put just this in my reaction container, I will get some of this, but some of this will be left over. If I put just this in my reaction chamber, you will end up with some of this and some of this. The point is, you end up with a certain proportion of this to this in your reaction chamber. And it doesn't matter what concentrations you start with these two. Right? You start with 0 of this and all of this. It's going to go to a proportion. Let's say, this really isn't quite true, but let me say, I'm at least going to do products over reactants. I'm going to put the product here on top. And let's say that equals 0.416. It doesn't matter if I have 0 of this and all of this. I let it go for a while. They're going to react, and then it's going to stop reacting when this proportion equals this. If I started with all of this and 0 of this, it will react this way for a little while until it lands here at this exact ratio. That means it's reached equilibrium. It always goes back to equilibrium. I could put a tiny amount of this and 10 times as much this, and still, regardless of how I started it, they're going to react such that they end up in this perfect proportion. And this is a constant. We can determine that experimentally. That's the idea. Let me do this. Let's say I've got a gas in here, and let's say it's reactants and products. And reactants and products are, and it's just sitting there. It sits just like that. Well, let's put it like this. I have reactants and products as a gas in here. I'm sort of magically separating them. So I've got product over here and reactant here, and the size is supposed to indicate how much of each. But yeah, they do mix up. But if I added up all the product versus all the reactant, let's say I have 75% this and 25% this. Okay, let's say I go up to another reaction vessel, and I mix it such that there's this much reactant and that much product. What happens is the reaction starts, the reactants start becoming products, and that starts moving this line over until it gets back to this line, and then it stops. It gets back to that equilibrium where there's 75% here and 25% here. And the same thing will happen if I start with products, just a little bit of products, and a lot of reactant. It'll react, but it'll react the other way. This line will move back to that point where there's 25% and 75%. And that point is the equilibrium point. What we're really saying is, relating to rates is, the forward rate and the backward rate become equal. You can change the proportions of what you have. If this forward reaction is going faster than this backward reaction, then you're getting less and less of this and more of this. Or if this is going, if this is going faster and this is going slower, then you'll get more and more of this while you get less and less of this. The point is it adjusts however it needs to get back to that magic number that is equal to equilibrium. Okay. That's the concept. What else would I say? Let's do this. I'll say the reaction constant, the rate constant forward, and the rate constant backward. So what we're saying is rate forward equals the rate backwards. Once they equal each other, that's when they're at this equilibrium point. That's really what's going on. It's not that the reaction stops. It's just you get just as much of this going this way, this way at any given point in time, and it ends up being at that equilibrium point. I guess I'll draw that. Okay. In general, we don't really use an equation this simple. The equation is a little more complicated than that. NA plus NB. So these are the coefficients for the reaction. XC plus YD. What we actually use, I'm going to say this, I'm going to say, we call this the reaction equation. Why the equation looks like this is a description well beyond what we're doing, but there is a generality to it that is easier to see into, but it's this, and you put the M there. No, I just did this backwards. It's products over reactants. So I need those on top. C, D, and then I'm going to put the X there and the Y there. So those stoichiometric coefficients go here as powers. But don't worry, we're not going to do lots of look at the graphs and figure stuff out like we did with rates. So it's just that equation. I don't mind giving you that on the test. It's very simple. That's for liquids. If you had gases, we would do it by partial pressure. Partial pressure of C to the X. Partial pressure of C to the X. Partial pressure of D to the Y, partial pressure of A, M, partial pressure of B to the N. So that's what it would be for a gas. But let me just use this equation for now. Look at the graph. Good graph. Guess I can just sketch it. Okay. There are actually ways to calculate the equilibrium constant, but we won't do that. That's high-level thermodynamics. But let me do this. I've got a reaction, time goes on, and let's say I put it together with what's a reactant? Yeah, very little product. So the generality I'm talking about, don't think about the powers. Just realize the more products you have, the bigger this number will be. And the less products you have, the smaller this number will be, the numerator. It's same for the reactants. If you have lots of reactant, this will be a big number. If you have a very small reactant, very little amount of reactant, that'll be a very small number. Can you see that? That's all the logic you really need to follow this. If I have lots of reactant and very little product, and I said I'm graphing Q here, so the reaction starts. So if I do have lots of reactant and very little product, what would you say about Q here? If you have very little, no, lots of reactant, big number for the denominator, a small number for the numerator, what do you think this would be? How would you describe that?
Small.
Small. I would even say fractional. I mean, you can have 1 over 2 and then 1.3 over 1.9 and then 1.5 over 1.8. And this is still less than 1. But if I keep making this bigger and I keep making this smaller, eventually you get to 1. You see what I'm saying? So I would say that's fractional. And then the flip side is if I have lots of product and very little reactant, then I'm greater than that. Then I can go on to 1 point something and 2 point something, and you can get all the way to huge, huge numbers. If this gets big enough and this is small enough. So I would say this is fractional, and if I was just going to graph it, I would go like this. I would start down low. I'm going to do that. Just for emphasis. The reason this levels out and then just goes forever, pretend that's a straight line, is because at a certain concentration products and a certain concentration reactants, it does stop. It does reach a point, I should have done this. It does reach a point where the forward reaction and the backward reaction are the same, so then they stay static. And that's the equilibrium point. So the answer to this equation, like what I'm saying is at this point, I look at A, I look at B, I look at C, I look at D, I get their concentrations, and based on the balanced reaction, I put that in, and I do a calculation, and then I get a number. So right there I did it, right there I did it, and that was Q, right there I did it, that was Q, right there I did it, that was Q. When I got here, it stopped changing. Whatever this equation came out to be, it just stayed that from now on. You follow that? Same thing would happen if I started with did this backwards, lots of product and very little reactant. Lots of product, very little reactant. Now I'm going to be some huge number, but this will still happen. It's still going to go and reach that straight line. Meaning this will get a little smaller, this will get a little bigger. This will get even a little smaller while this gets a little bigger. A little smaller, a little bigger, until it hits that magic point of equilibrium. The equilibrium constant is the value of Q at this point. That's the equilibrium constant. It can be calculated from thermodynamic data, but that's the concept. And I'm going to stop there for test 1. This is where we'll pick up for test 2. But look at this kind of question you might get, and this is very simple. Exercise. This is easy. question is, make the equation for the reaction quotient, meaning this, Q equals products, concentration of free product to over reactant. That's the answer to the first one. The second one, Q equals product NH3 to NH2, H2, 3. See what I'm doing? And then for the last one, products, concentration NO2, fourth power, concentration of H2O, 6 power, products of the reactants, NH3. So equals Q. Yeah, I think that's as far as we'll go in equilibrium. The rest of it is me getting questions online. We'll review some on Friday, and I guess we'll review some on Monday. We'll do lab 4 on Wednesday. So we will do a lab. It's a kinetic lab.